Fine. You all try to answer this question. A work of, let's say, 100 joules is done by a constant force during a displacement of 20 meters. Okay. Displacement of the point of application of the force itself. Okay. That is 20 meters. The question is, how much is the force? How much is the magnitude of the force? Simple question. Work done is given, displacement is given. You are asked the magnitude of the force. I got one answer as 5 and I got one response as another question. Good. Venla, how did you say it is 5?
So work done equal to force into displacement. F dot S, sir.
Dot product. Okay. Okay, that's the correct way to say it, F dot S. But how did you conclude that the force will be 5 Newton? What is the formula for dot product, A dot B?
Fs cos theta.
Yeah, AB cos theta. So here it becomes Fs cos theta. Now in the question you are given the amount of work done, you are given the displacement, but you are not given the angle, and without that you cannot calculate the force. Okay, they said it's a constant force, but they didn't mention at what angle it is acting with the displacement. Okay, Saket, the question you asked is correct. Okay, are they in the same direction? You need to know, or what is the angle between them? You need to know. Okay. Now, if I ask you, like in the same question, like force you cannot tell, but if I ask you, how much is the tangential force, magnitude of tangential force? Can one of you tell me what is the meaning of tangential force? What do we mean by tangential force? The force acting parallel to the displacement. Okay, or the component of force acting parallel to the displacement is what we call as tangential force. Tangential force gives tangential acceleration, changes the speed. We have discussed all this. Can you calculate tangential force in this case? How much force acted parallel to the displacement? This is all simply based on the basic formula for work. I got one answer as 0. If tangential force is 0, then who did the work? Or what force did the work? Okay, work done is non-zero, no? Tangential force cannot be 0. Okay, fine. Listen. Again, like basic dot product definition only. Suppose there are two vectors. Okay, wait, I got one more answer. Saket is saying if it is perpendicular to displacement, theta is 90. I said tangential force is the force parallel to displacement. Did I say perpendicular? Other students, did I say tangential force is force perpendicular to displacement?
No, sir.
I don't think so. Okay. Yeah. Tangential force is the component of force along the displacement, means parallel to displacement. Okay. So let's say there are two vectors A and B with an angle theta between them. Okay. We all know that A dot B by definition is AB cos theta. Okay. This can be treated as A multiplied with B cos theta. Now understand what B cos theta means. B cos theta is the component of B in the direction of A, or we can say component of B parallel to A. Okay, so you can treat the dot product as A multiplied with component of B parallel to A. That can be done. You can also consider the dot product like this. AB cos theta is also equal to B multiplied with A cos theta. Mathematically, it's the same. A into B same as B into A. This is simple multiplication. Okay, we have removed the dot product. Okay, what's on the right hand side is normal multiplication. So it doesn't matter which term you multiply first. Okay. Understand what A cos theta means. A cos theta is the component of A parallel to B. This is what is A cos theta. So we can call it A parallel, the component of A parallel to B. Okay. So dot product can also be taken as B vector multiplied with component of A parallel to B. Now we know work done is F dot S. So you can treat this as force, magnitude of force multiplied with displacement parallel to force, or you can also treat it as displacement multiplied with force parallel to the displacement, and force parallel to displacement is what we call tangential force. That's all. We know the work done is 100 joules in a displacement of 20 meters. Multiply that with the tangential force. So the component of force in the tangential direction is 5 newtons. We don't know the actual force that acted on the object, but in the direction of displacement, it would have experienced a force of 5 Newton. That much we can tell for sure. Okay. So basically in this question, what we get to learn is how to calculate tangential force based on work and displacement. So you can tell how much force acted in the direction of displacement. Perpendicular to displacement, you can't tell how much force acted based on work. Okay. And this is a very important idea. What we are now going to do is work on this a little bit. We'll try to do, we'll try to find out force from work and displacement. Okay. Now, see, if the force is constant, then we can simply answer it like this. We can divide work by the total displacement to get the constant force that acted throughout. Okay, at least in the direction of displacement we can get. Suppose the force was variable, then it gets complicated. Okay, can one of you tell me the formula for work done by a variable force? Nothing new we had discussed earlier. Or the general formula for work, which will always give you an answer.
Integration of Fs
Okay, don't say Fs.
cos theta.
Integral F dot. No, it's still not correct. It is integral F dot ds, small displacement. Okay, and that becomes integral F ds cos theta. So basically what we are doing here is we are first considering a small amount of work over a small displacement ds. So dw simply becomes F dot ds. Now, over an entire displacement, maybe from initial position A to final position B, the force can change from point to point. But ds is so small a displacement that the force cannot even change significantly over that displacement. Okay, so we'll use F dot ds for small displacements. Very, very small. Okay. Now, F dot ds is basically a dot product between two terms, two vectors, right? So this becomes F ds cos theta, you can treat it as force multiplied with displacement parallel to the force. You can take it like that. Or you can treat it as displacement multiplied with the force parallel to the displacement. Can be treated like that also. So now we have removed the dot product. By taking parallel components and multiplying, we have removed the dot product. Therefore, the parallel force can now be written as dW by ds. Small amount of work done divided by small displacement. That gives you the component of force along the displacement. It gives you F parallel. That is the component of the total force acting along the displacement ds. Okay, this is how we will extract force from work. You differentiate work with respect to displacement, not with respect to time. With respect to displacement, if you differentiate, you will get the tangential force. Okay, so tangential force acting on an object at any instant is dW by ds. There is another way also to justify this, or to derive this also, I can say. Work dW from work kinetic energy theorem, work done is equal to change in kinetic energy. So we can write dW, small amount of work done, is the small change in kinetic energy. But this is valid if you are considering work done by all forces, okay, or the net force on a particle. That can be written as small change in kinetic energy. Formula for a particle is half mv square. Okay. Therefore, you can write dW by ds, small displacement. Okay, you can call it dr also, nothing wrong in that. R is position, dr is small change in position, that itself is small displacement, you can call it like that, is equal to derivative of half mv square with respect to r. Okay, let's differentiate this. Half and mass of the particle are constants, so you'll have to differentiate v square with respect to r. Can one of you tell me what is the derivative of x square? What is the differentiation of x square with respect to x?
2x, sir.
2x. Okay. Then what is the derivative of x square with respect to some other variable, say time? You are differentiating one function, or you are differentiating a function in one variable with respect to some other variable. What rule of differentiation should you apply, and what is the answer? Okay. Derivative of x square with respect to some other variable t can be considered like this. Derivative of x square with respect to x, because that's what you know to do, and multiplied with dx by dt. That's all. Mathematically, they are the same. So that becomes 2x into dx by dt, chain rule of differentiation. Okay. You all have to revise this a little bit. Fine. I'll include some problems based on this. So now come back to dw by dr. dw is small change in kinetic energy, which is d of half mv square. D indicates small change, okay? So d of half mv square means small change of kinetic energy. So you need to differentiate v square with respect to r. So that becomes half m. V square derivative, or dv square by dr, can be written as d of v square by dv multiplied with dv by dr. So derivative of v square is 2v and dv by dr. Okay, 2's get cancelled. You will be left with m into v dv by dr, and okay, dv by dr. And if you all remember, dv by v dv by dr is nothing but tangential acceleration. Okay. Like how did we get this? Motion in a straight line. Equations of kinematics. While deriving, we write A is equal to V dV by dr. Send dr this side. Integrate both sides. If A is constant, it comes out. Integral dr becomes displacement. V dV integral is V square by 2. From initial to final, you get V square minus U square by 2. So V square minus U square is 2as. Okay, in the derivation we discussed. Now, in the formula for kinetic energy, V stands for speed. So V dV by dr stands for tangential acceleration. And mass into acceleration is nothing but force. So this whole thing becomes tangential force. What was on the right left hand side? Derivative of work with respect to displacement or with respect to position. It's the same thing. Gives you tangential force. Okay. Earlier also, that's what we had derived. From the definition of work we derived. Now we derived it from work kinetic energy theorem. But the takeaway from this discussion is that the tangential force acting on an object at a particular instant is the derivative of work done on it with respect to displacement or with respect to position. ds and dr are the same. ds stands for small displacement. Small displacement is a small change in position. They are the same. Okay. Can one of you tell me, by definition, how is change in potential energy calculated? I'm not asking gravitational or spring or particular cases like that, but by definition, like in general, how is change in potential energy calculated? When you solved the worksheet based on potential energy stored in a spring, what was the idea we used there? Delta U is equal to?
Minus work done by force.
Correct. Negative of, by definition, change in potential energy of a system is negative of work done by the conservative forces acting on that system. Okay. So a small change in potential energy can be equated to a small amount of work done by the conservative forces. Okay, this is the definition of change in potential energy. Now differentiate, or not different, just divide by dr on both sides. What do you get? Du by dr is equal to minus dw by dr. Now dw by dr is nothing but tangential force. So this is nothing but force in the direction of dr. Force in the direction of displacement. Okay. So this is the basic relation. I'll write it this way. Force, okay, I have to mention in the direction of dr because this is not the net force. Force in the direction of dr is equal to minus du by dr. This is a very useful relation. Basically, this equation relates force to potential energy. Okay. But remember, this equation has its own limitations. By differentiating potential energy and adding a negative sign, you can only get how much force is acting parallel to the displacement. You can't get the overall force on the system or the particle. Okay. Now, mathematically, this equation is written in a different way. Okay. Now see, you are differentiating U, that is potential energy, with respect to R. R is nothing but position. Okay, or dr is a change in position in a particular dr is a small displacement. No, it will have a fixed direction, right? Now consider motion in a plane itself. Motion in a plane is basically two-dimensional motion. When an object moves along the x-axis, one of you tell me how much is its displacement in the y direction? If it's purely moving along the x-axis, how much is the displacement along the y direction? Yusuf, what do you say? If an object is moving along the x-axis,
So 0?
0, correct. It's not moving in the y direction, no? So for this kind of displacement, you can say dy is 0, dx is non-zero. Okay. Next case, if an object is only moving in the y direction, maybe positive y, maybe negative y, let it be, you can clearly say, you can easily say that the displacement in x direction is 0 for this. It's only getting displaced in the y direction. Fine. So basically the idea is that if an object is moving in a particular direction, then its displacement in a perpendicular direction is 0. Obviously, we don't even have to prove it. A vector's component in a direction perpendicular to it is 0 because a cos theta becomes 0 when theta is 90 degrees. So this equation that we have written here, force in a particular direction is minus dou u by dou r, where you have to differentiate along that direction. Okay? Mathematically, it's written this way. Suppose consider the x direction. We know force in the x direction is minus du by dx. Okay. So if the displacement is in x direction, you get the force which acts along the x-axis from this equation. That is known to us now. But when you are moving along the x-axis, you have to consider y and z coordinates to be constant. Okay, we know that if something is moving in the x direction, then it doesn't get displaced in the y direction or the z direction. So if you want to find out force in the x direction from potential energy, you will have to differentiate potential energy with respect to x. But while doing that differentiation, you have to assume y and z to be constant. Okay. Now you may ask, sir, why are y and z even being considered? Why should we treat them to be constant? Where are they? Okay. We'll solve problems, you'll understand. But remember, to get force in a particular direction, you have to differentiate potential energy with respect to displacement in that direction. And when you are getting displaced in that direction, your displacement in the perpendicular directions will be 0. Means the perpendicular coordinates won't change. Like if an object is moving in the x direction, its y coordinate won't change, z coordinate won't change. So y and z will be treated constant. Okay. Mathematically, this is called partial differentiation or partial derivative. Okay. And there is a separate symbol for it, very similar to d. It's called dou. We write force in the x direction is minus dou u by dou x. Okay, it's called dou. DOW, DOU, whatever. Okay, dou stands for partial derivative. D stands for normal derivative, the usual differentiation that we do. Let me explain the difference with an example. So basically what we now have, or what we are now doing, is calculating force from potential energy. Okay. So suppose you are given potential energy as a function like this, x square plus y square. So it depends on both x coordinate and y coordinate. It's possible. Okay, when an object moves in the along x-axis, potential energy is changing. When it moves along y-axis, also potential energy is changing. Let it change. Okay. Now, what gave rise to this potential energy and all is immaterial to us. You are given a potential energy function like this. Okay. So from the function, you can tell that if the x coordinate changes, the energy will change. That means if the object moves along the x-axis, there is work being done on it. Obviously, for energy to change, work has to be done, no? And energy depends on x coordinate, means work is being done when the x coordinate changes. Okay. Similarly, energy also depends on y coordinate, means work is being done as the y coordinate changes, means when object moves in the y direction also there is work being done on it. So from this we can conclude, based on the fact that energy depends on both x and y coordinates, we can conclude that there must be forces acting along x direction as well as y direction on the object. Obviously, when object is moving in the x direction, work is being done on it, means there must be a force having a component in the x direction. Okay. And when object is moving in the y direction, also work is being done on it. So there must be a force component in the y direction as well. Both are there. Suppose you want to find out the x component of the force. Then what you'll have to do is, you'll have to take the negative of derivative of potential energy with respect to x, but you will need to assume y to be constant. Okay, I don't have to say that, or wait. If I write the usual derivative d symbol, okay, using d, then I'll have to tell you that y is constant. But differentiating with respect to one variable, treating the others to be constant is what you call partial derivative. So I can directly write it this way. Okay, so this means this. Differentiate with respect to x, treat y or any other term as constant. Okay, let us do that. The function u is x square plus y square. We need to differentiate x square plus y square with respect to x. Okay, see, usually it is supposed to be done like this. This is differentiation of two functions being added. You can split it into two separate different derivatives. Dx square by dx, that is derivative of x square, plus the derivative of y square with respect to x. Derivative of x square is 2x. Derivative of y square with respect to x is 2y dy by dx. This is the proper way to differentiate this function, by treating x and y both as variables. But if you want to partially differentiate this, okay, if you want to do partial derivative of this function x square plus y square only with respect to x, you will have to treat y as constant. Okay, split this into two terms first. That is derivative of x with respect, okay, derivative of x square with respect to x plus the derivative of y square with respect to x. Now we have to treat y as a constant because we are doing partial derivative. Now if y is a constant, can one of you recollect and tell what is the derivative of a constant? What is the rate of change of a constant?
0, sir.
0. Then this term becomes 0 and the answer will only be 2x. Instead of 2x plus 2y dy by dx, you only get 2x. That's the difference between usual differentiation and partial differentiation. Okay, in usual differentiation, all the variables will be differentiated. In partial derivative, you'll take only one variable. Even if y is present, you'll treat y as a constant number. If z is present also, you'll treat z as a constant number. That is the difference between the usual differentiation and partial differentiation. Okay, and where did the need for partial differentiation arise? It all came from the definition of work for us in physics. Okay, work by definition is force multiplied with displacement parallel to force, or displacement multiplied with the force parallel to the displacement. So work considers only the tangential force, and the force in the direction of displacement is what you need to consider. So when moving in a particular direction, we know the other coordinates will be constant. The perpendicular coordinates will be constant. So if you want to find out force from potential energy, you will have to do a partial derivative of potential energy with a negative sign. So in this case, let's proceed. We got dou u by dou x. We got it as 2x. Now we need to put a minus sign to it. Therefore, force component in the x direction becomes minus 2x. Minus dou u by dou x, that is minus 2x. Okay, dou means partial derivative. Fine. Similarly, you can calculate the y component of the force also. And because x component and y component are similar, you can directly tell that the force in the y direction will turn out to be minus 2y. Okay, so that way we can get force from potential energy function. That is what was given to you in this problem. Try another question like this, all of you. Suppose the potential energy function is x square plus 2xy. Okay. Now, as you can see, it depends on x coordinate as well as y coordinate. Means when you move in the x direction, potential energy changes, means work is being done, means there is a x component of force. Similarly, when you move in the y direction, y coordinate changes, and if y coordinate changes, this potential energy value is going to change. Means work is being done even when object moves in the y direction. Means there must be a y component of the force as well. Find out the components or derive the components. How much is the x component of the force and how much is the y component? Right? I'll write the formula also. It is negative of partial derivative of potential energy with respect to x, and the second part is negative of partial derivative of potential energy with respect to y. And you know what partial derivative means. Just differentiate, but treat all other variables as constants. Okay, vanilla, your answers are correct only. Okay, let us discuss. Pawan, how are you trying to solve this? Or do you have any answer?
Sir, first one ki 2x minus 2x.
First one you are saying is minus 2x. Let's see. So negative sign, put it aside. You need to differentiate. In fact, you need to differentiate partially x square plus 2xy. Okay, we'll split it into two terms directly. So you need to take partial derivative of x square plus the partial derivative of 2xy. Okay. Pawan, what is derivative of x square with respect to x?
Sir, 2x.
Okay. Minus sign will stay. First part becomes 2x. Okay. What about this?
Right, sir. అంటే దానికి product వాడాలని డౌట్ వచ్చింది సార్ నాకు.
Okay, you got the thought that maybe product rule has to be used. When do you use product rule generally?
సార్ అర్థమైంది సార్.
Hmm?
Product వాడకూడదు సార్. అది 2 వేరియబుల్స్ ఉన్నప్పుడు వాడాలి సార్. కానీ ఇక్కడ y కాన్స్టెంట్
When there
కాబట్టి
are two variables being multiplied or when there are two functions being multiplied, you use product rule, correct? Yeah, and what you said after that is also correct. We are doing partial differentiation with respect to x. So y will be treated as a constant. And 2 is already a constant. And what do we do with constants in differentiation and integration? We put them outside. So 2 and y you bring out. If you bring out 2 and y, you will be left with derivative of x with respect to x. Pawan, how much is derivative of x with respect to x?
సార్ 1.
1. Okay. So the x component of the force becomes negative of 2x plus 2y. Okay. Yusuf, is this clear?
Yes, sir. Yes.
Okay. Can you tell me the expression for force in the y direction, Yusuf?
So minus 2x square by 2. It's a differentiation. Like directly next one. So minus 2x square by 2x plus 2y, sir, plus 2x y by 2y.
Okay. Call it dou. Okay. Dou of x square. Okay, dou x square by dou y. Okay, when you said it, it heard like I heard it like 2x square by 2y. Okay, dou x square by dou y. That's the partial derivative of x square. And then you have to take partial derivative of 2xy with respect to y. Okay, fine. How much is this now? Partial derivative of x square with respect to y. How much will that be? Listen, all of you, if you are taking partial derivative with respect to some variable, okay, like here we are differentiating with respect to y, every term other than y will be considered constant. Now, in this bracket, there is no y at all, there's x square. X will be treated as constant, so x square is also a constant. So effectively, this part becomes derivative of a constant. Use of how much is the derivative of a constant? Rate of change of a constant. Zero. Constant does not change. Okay, its rate of change is 0. Next, second term, you will have to differentiate 2xy with respect to y. Okay. The thing you are differentiating is 2xy. 2 is a constant anyway. And since you are doing partial derivative with respect to y, x will also be considered a constant. And what do you do with constants in differentiation? We put them outside the derivative. So this becomes negative of, first term is 0. Second term, 2x stays outside the derivative. What's inside the derivative is dou y by dou y. And dou y by dou y is 1. Derivative of y with respect to y. So minus of 0 plus 2x, the answer is minus 2x. That's the y component of the force. And we got these from the potential energy function. Yusuf, is it clear?
Yes, sir, clear, sir.
Okay, okay. Pawan, did you understand?
Yes, sir.
Fine. So if you take partial derivative of potential energy in a particular direction and put a negative sign to it, you get force in that direction. You get the component of force in that direction. Now we got both the x component and y component of the force. Then we can express the complete force at once, like in one equation. You can write it as negative of 2x plus 2y. This was the x component of the force, no? So I cap. And negative of 2x. This was the y component of the force, so j cap. That way you can write the entire force equation. Fine. So from potential energy function, you can calculate or you can derive the force equation. So force and potential energy are related to each other. Obviously, potential energy arises when there is a conservative force present or when the conservative force does work. Okay. Now, in the classes before this, we calculated change in potential energy and all based on the force. Now we are doing the reverse. Based on potential energy, we are deriving the force. Fine. Can one of you tell me the definition of equilibrium? When is an object or a system said to be in equilibrium?
That net equal to zeros.
Correct. Okay. A system or an object is said to be in equilibrium when the net force acting on it is 0. And this is called as translational equilibrium. There's something called rotational equilibrium also, which we'll learn in the next chapter. For now, you consider this as the definition of equilibrium, net force being 0. Okay. Now tell me this, one of you. By looking at an object, can you tell whether it is in equilibrium or not? Like by looking at or by observing an object for some time, can you tell whether it is in equilibrium or not?
Yes, sir.
How? Like, Yusuf, can you mention any object which is in front of you?
So my pen.
Okay. Is it in equilibrium or not?
So looks like it's not moving. It's completely rest.
Okay. So it's at rest. I mean, for the duration that you observed, it was at rest. So you said it's in equilibrium. Okay. And that's correct also. If an object is at rest and it continues to be at rest, then we can conclude that the net force on it is zero. Simply being at rest for one moment is not enough. It should continue to be at rest. Then you can say that net force is zero, it's in equilibrium. Fine. What about moving objects? Can a moving object be in equilibrium? Vanilla.
Sure.
Can a moving object be in equilibrium?
Yes, sir.
How should it be moving?
With constant velocity.
Correct, correct. See, net force is zero means acceleration is zero. Doesn't mean velocity is zero. So an object moving with constant velocity is also said to be in equilibrium. So it can be at rest and continue to be at rest, or it can be moving and continue moving the same way. Then we say it's in equilibrium. So if an object continues doing what it is doing, it's in equilibrium, be it rest or motion. Okay, fine. Now consider three different situations like this. Okay, suppose there is a bowl. Wait. And let's say there's an inverted bowl. Okay, just a surface shaped like this. And in the third case, let's say there is a horizontal surface. Right. These are all rigid surfaces. Okay. So side view looks like a curve like this. Consider a ball here. And okay, that's at the lowermost position in that ball. And consider a ball here exactly at the topmost position. And consider a ball here on this surface. Let's call them cases A, B, and C. The ball in case A, is it in equilibrium or not? We placed it there and left it. Will it be in equilibrium or not?
Yes, sir.
Okay. What forces act on it? Or are there no forces at all?
Mass and normal. Weight and normal, sir.
Okay. Weight and normal force will be acting. Weight acts vertically downward. Normal force from the curved surface acts upwards. They'll balance. Net force is zero. It's in equilibrium. We know from everyday experience also, you put an object there, it will be at rest. Okay. It will continue to be at rest. So this is a case of equilibrium. Okay. Next case. There is an inverted U-shaped surface like this. Okay. Or inverted bowl-shaped surface. And we carefully place the object exactly at the topmost point. Will it stay there or not? In an ideal case, you assume the surface is perfectly shaped, no roughness, no ridges and grooves, perfectly shaped surface, perfectly shaped ball. We kept it at the topmost point. Will it stay there or not? Pawan, what do you think?
Sir, no.
Tell me what forces act on it after we leave it.
Sir, gravity and weight.
Hey, gravity weight రెండు ఒకటే సరిగ్గా చెప్పు.
Sorry, normal and weight.
Weight and normal. Weight acts vertically downward. Normal force, which way will it act?
Sir, upwards.
At that point, the surface is horizontal. So normal force acts upward. Then, Pawan, which way do you think it will move? You said it won't stay there. Will it move to the right or to the left? Or will it jump up?
సార్ అలాగే సార్ నార్మల్గా ఇప్పుడు చూసాను నేను అలా పెట్టి చెప్పాను.
No, no, you said based on everyday experience. But in everyday experience, like in daily life, the surfaces are not perfect. Okay, they are not perfectly smooth surfaces. At the molecular level, ups and downs will be there on the surface. But I told you that this is a case where the surface is perfectly shaped. The ball is also perfectly shaped. Okay. And you said these are the forces acting. No, both forces are vertical. There's no horizontal force. Then why should the ball move horizontally? Okay. So in a perfect
Yes, sir.
situation, in an ideal situation, this ball will not move. You place it there, it stays there. Okay. Others, are you convinced with this or not? If you think that it will move, you'll have to tell why it moves. Okay. Now, in a real life situation, if you try to balance something like this, there's a chance that it rolls off or slides off. Because in a real life situation, let me separate the surface from the ball. In a real life situation, this surface will have some roughness like this at the molecular level, at least. Okay. Even the ball's surface will have some roughness. Okay. So depending on how the ball is placed, how the molecules of the ball interact with the molecules of the surface, the normal force may act at an angle like this or at an angle like this. It's very hard to place it in such a position where the normal force acts exactly in the vertical direction. That's why in a real life situation, most likely the ball will slide off or roll off either side. Okay. So in an ideal case, it will stay there itself. Ideal case means perfectly shaped surfaces. It stays at the topmost point when you leave it there. So second case, is it a case of equilibrium or not? It's at rest, it continues to be at rest, therefore it is equilibrium. Net force is zero, weight and normal force are balanced. Okay. Third case, it's obvious. You leave the object there, it stays there itself because the surface is not inclined. Why will it start moving? Okay. Weight acts downwards, normal force acts upwards. They are balanced. There's no reason why the object should move. So third case is also a case of equilibrium. Okay. But there is something different about these three situations. In the first situation, first case, you take the object, the ball, to the immediate next position, maybe somewhere here or that side. Okay, next position. When it is at the next position, I'll show it in gray. Okay. So one of you tell me, if the ball is shifted to the position just to the left of it, okay, on that curved surface, and released from that position, will it have a tendency to come back to equilibrium position? Will it have a tendency to go away from equilibrium position? Or will it again be in equilibrium there? Will it stay there? What tendency does it have? What will it do?
Come back to equilibrium position.
Obviously, it will roll down. It will try to come back to equilibrium position. Even when you put it on this side, okay, it will have a tendency to come back to equilibrium. So the first system, the ball, okay, if you disturb it slightly also, it has a tendency to come back to equilibrium. Fine. This kind of equilibrium is called stable equilibrium. Okay. Even if the system is disturbed a little bit, it should have a tendency to come back to the equilibrium state, equilibrium position. That kind of equilibrium is called stable equilibrium. So basically, whether the equilibrium is stable or not will be determined by what happens when the object is taken to positions around the equilibrium position. Okay. Exactly by looking at this, you can't tell whether it's stable equilibrium or not. You need to know the surroundings. You need to know about the surroundings. Then you can decide whether it is stable equilibrium or not. Okay. Next case. If the object is taken to the next position and released, okay, it's obvious. Will it come back to equilibrium or will it go away from equilibrium or neither? Okay. You don't even have to say it will go away from equilibrium. So second case, we have identified an equilibrium position, but when the object is disturbed even a little bit from equilibrium and released, it has a tendency to go away from equilibrium. That kind of equilibrium is called unstable equilibrium. Okay. So if a system at equilibrium is slightly disturbed and released, and it has a tendency to go away from equilibrium position, that equilibrium is called unstable equilibrium. That kind of equilibrium is called unstable equilibrium. Next, third case. Again, here you don't even have to say. You disturb the particle a little bit, means take it to some other position around the equilibrium position and leave it. Will it have a tendency to go away from equilibrium towards equilibrium or neither? In this case, it is neither. Okay, that kind of equilibrium, like even if you disturb the system a little bit, or if you disturb a system a little bit, it should neither have a tendency to come back to equilibrium nor have a tendency to go away from equilibrium. That kind of equilibrium is called neutral equilibrium. Okay, so there are three different kinds of equilibrium depending on what happens if the equilibrium is disturbed or if the particle is disturbed from equilibrium. Okay, so stable, unstable, neutral. And there is a mathematical way of identifying these. Fine. Now, let's consider these cases itself. In the first case, when you disturb the particle away from equilibrium, okay, see equilibrium position, I'll mark it as O. When you take the particle away from O, you're taking it higher, means you are increasing the potential energy. Okay, from the equilibrium position, when you disturb it, you increased its potential energy. That means the equilibrium position, at the equilibrium position, the object had minimum potential energy. Away from equilibrium, its potential energy is increasing. At equilibrium, it has the least potential energy. We are talking about gravitational potential energy here. If height increases, that increases. Second case, when you take the object away from equilibrium along that surface, you're actually bringing it down. If you're bringing it down, you're decreasing its potential energy. That means at the equilibrium position, it had maximum potential energy at equilibrium. Okay. First case, it had minimum potential energy at equilibrium, that is stable equilibrium. Second case, potential energy is maximum at equilibrium, that is unstable equilibrium. Third case, whether it is equilibrium position or the position to the left of equilibrium or the position to the right of equilibrium, they all have the same potential energy. The particle is neither going up nor coming down. Okay. So we say that this is neither a maximum nor a minimum. Or, okay, you don't even have to make it so lengthy. You can just say constant, not even constant. There's a difference. You have to say uniform potential energy. Means at that point and the surrounding points, the potential energy is same. We say it has uniform potential energy. So based on what is happening to the potential energy of an object when it is moved away from equilibrium, you can tell what kind of equilibrium it is. Okay. When the object is moved away from equilibrium and you see potential energy increasing, then that is stable equilibrium. Okay, when it is taken away from equilibrium, energy is increasing, means at equilibrium the energy was the least. So that is stable equilibrium. Next, at equilibrium, if you see that the potential energy is highest, but at surrounding points the potential energy is lesser, then it is called unstable equilibrium. Third case, whatever is the potential energy at equilibrium position, same is the potential energy at surrounding positions also, then you call that as neutral equilibrium. Okay, so how do we mathematically find out whether the equilibrium is stable, unstable, or neutral? The hint lies in what happens with the potential energy. Minimum potential energy, maximum potential energy, constant, or okay, I should not say constant, uniform potential energy. Now, I want you all to revise. When we discussed, I want you all to revise maxima and minima. When we discussed differentiation, okay, we learned how to find out the maximum value of a function using derivatives and how to find out the minimum value of a function using derivative. Okay. So I want you all to revise that a little bit before the next class. I'll include some questions based on this in the worksheet also. Tomorrow early morning you'll get one worksheet. By evening you solve. Okay. So revise how to calculate maximum and minimum value of a function using differentiation. If you know how to do that, then identifying what kind of equilibrium it is becomes very easy for you. Okay. Fine. We'll stop it here for today. We'll continue in the next class.